So good morning, everyone. Today we have the pleasure to have with us Yuan Tian, visiting us from UCLA. Just a reminder for people in the room and online that this is a proper data seminar. It's a hybrid. That's why all the technical problems to set it up. We have people in person. We also have people online. So on the general topic of privacy. So Yuan joined UCLA very recently this year, right? Last year. All right. And before that, she was an assistant professor at the University of Virginia. And before that, she finished her PhD at CMU. She has done a lot of great work in the general area of security and privacy, especially on emerging platforms. And that's the topic she's going to present today. One interesting aspect about Yuan's work is that it crosses the boundary between CS and policy and law. And that's why in UCLA, you're also affiliated with the Institute in Technology, Law, and Policy, right? All right. So, and I mean, people know your work. I don't need to say more. You have gotten all the awards that a person at your stage can get, including the Google Research Award, an Amazon AI Award, and so on. So, without further ado, thank you for visiting us, and looking forward to your talk.
Thank you so much. Thank you so much, Asena, for introducing me, and thanks everyone for coming to my seminar, especially it's a raining Friday morning. And also thanks to the ones for joining me online as well. So today I want to share about our recent research regarding towards regulated security and privacy in emerging computing platforms. And I also hope to. Is there more questions during or only after? Feel free to interrupt me for clarification questions.
Yeah. All right. So for questions, if you have questions from the online world, raise your hand in Zoom and I will let you know.
Okay.
And in person, just raise your hand. Thank you.
Okay, great. All right. So basically, I also hope to discuss with you regarding this very interdisciplinary and also very exciting area of research across regulation, law, public policy, and lots of computer science and computer engineering research. So nowadays, computing is undergoing several significant shifts. So first is that the explosive growth of Internet of Things enables new ways of interacting among humans, computers, and physical world. This including our smart home sensors, smart building sensors, and smart vehicles. So now the way that we interact with the physical environment and also the computing systems also change a lot. The second is that machine learning algorithms are powering many applications and services, especially in recent years, given the explosion of large language models. These machine learning algorithms, they are making critical decisions, and they are also requiring a large amount of data, which naturally drive to the question about privacy. And finally is that nowadays our computing system no longer isolated, but we have complicated interactions among different applications and services. So putting this all together, these complex systems are prone to security errors, let alone privacy violations. So this trend brings more functionality and drastically increase the number of untrusted algorithms, implementations, interface, and the amount of private data that's being processed by them. Okay. So to address these issues, there have been lots of advancements in privacy regulations, such as GDPR, which is for European Union, and also CCPA, which is for us in California. So they majorly regulate two parts. The first is that they protect the data, basically the way data is being processed, being collected. Second, that they emphasize on the user consent and transparency, which means that they define data objects, the user's privacy rights, to have full control over the data, such as consent, right to erase. So the question is that, do these privacy regulations really address the problem? Okay, what's your answer for this question? Do you feel better protected for your security and privacy? Yeah, So I saw quite a few people shaking their head. So indeed, the answer is no, because there's a huge gap between the security, privacy, or ethical properties and the reality. So basically, the security and privacy and ethical properties depends on what regulations request, what protocols specify, and what users expect. But in reality, it really depends on how the developers understand these regulations and how they actually implement in the systems. So for my research, I've been looking into how to bridge the gap. So I proactively check the privacy and security violations in the emerging systems. Let me give you a few examples from my previous research. First, let's look into privacy violations. For example, this is a piece of news report about our research on voice device security. Voice device security and privacy. We found that the design of voice control platforms actually allows them and also applications running on top of them to basically being a spy in a home. So there have been changes in Amazon Alexa and Google Home after our research. So basically, this is just one example. There are also a more like privacy violations in the wild world. For example, this is another example. Have you actually trying to configure privacy settings inside your applications? So note that this is not the general like privacy settings like the permission systems you use in Android or iOS, but this is inside one application. Like for example, for Facebook, you can actually configure who can send you message and who can search your name. So actually in our research, we actually automatically identify lots of hidden privacy settings, which are very difficult to be found by users and very difficult to use. Like around half of the privacy settings are hidden. So it's actually takes around 10 clicks to actually get into the privacy setting. And for these privacy settings, mostly around 82% of these privacy settings actually by default are turned off. So, and we even identify some privacy settings in WeChat, which is very popular Chinese social apps. After, even if you configure some privacy settings, after 3 months, they will revert it back. So basically, Google also got a large fine because of the unclear privacy settings. Just I think last year, still regarding this issue. So there are a lot of widespread issues regarding privacy violations. The question comes from lack of understanding regarding the privacy regulations, and also the motivation for more functionality, like better accuracy for the ads predictions. So there have been lots of conflicts between privacy and utility for these companies. So that naturally leads to privacy violations. So when it comes to security properties, things could even be worse. That's because security properties could be very complex and difficult to understand. So developers might not really know the security implications of the design in the specifications. Here also show 2 examples to show the widespread pervasive vulnerabilities. So we have a series of work with single sign-on security for the authentication part. We identify like 60% of apps actually make at least one security mistake. That allows attacker to be able to log in on behalf of the user, which is very dangerous. So this research also had impact over the IETF standards for our security suggestions. So time fast pass from mobile to IoT space. So basically we're also looking to the IoT messaging protocols, which I also talk more about later. You might be surprised, like we look into, I don't know why the figure was not displayed because we are using Google Slides, but in my slides, there's a figure of actually the 9 leading IoT platforms, including Amazon and also Google and Microsoft. So basically all these leading IoT platforms have at least one vulnerability which impact millions of users using them. So basically, all the major leading IoT platforms had done it wrong and have security violations. Okay, now it's displayed. Yeah. Okay, so before that, we were talking about, given the current privacy and security regulations, we are proactively looking into security and privacy violations. Now but that's still under the assumption about GDPR and CCPA, where we actually trust the companies to handle our data based on regulations. What if in some situations, the stake is so high, like for example, for the medical applications, for the financial applications, when we don't want to trust the company for handle their data because you saw so many violations, so many mistakes. So researchers have been working a lot on technologies in applied crypto, such as secure multi-party computations and homomorphic encryptions, homomorphic encryptions for this privacy-preserving techniques, especially for privacy-preserving machine learning. But the biggest challenge is the scalability. So here is the example, like if we don't have any privacy, so training SNet model on tiny ImageNet will take you 8.5 hours. This is on the basic CPU setting. So I also want to ask you to guess, what would the number look like with privacy? How long do you think? If we use this crypto technologies such as secure multi-party computations to actually protect the machine learning algorithms, that we don't have to share the data directly, but we can calculate and train the model and classifications on the encrypted data. How slow do you think that would be?
Maybe like till the end of the world?
Yeah, we'll have two answers. That's two extremes. So thanks for answering the question. And actually, the hint is that I actually use log scale for the comparison. So basically, it's actually around 1,000 times. So it takes around 1 year. So basically, it's not practical at all, even with so many constructions in recent years. So basically, this most of the technologies only work on toy examples and cannot really be used. Right? So let me summarize about the challenges to bridge the gap between the security and privacy regulations and the real secure and privacy preserving systems, especially in emerging computing systems. The first is that the new security and privacy implications for the new interfaces and technologies usually takes longer for people to understand than a real regulation has been in place. Second is that the security specifications are not well defined. So developers have a hard time really implement secure systems because they don't understand what are the most critical things for security. And also the systems keeps getting larger and more complex over time. So we need to look into the interactions between the different components in the systems to have a comprehensive security and privacy framework. And finally, we have diverse and closed-source implementations, which makes it even harder to actually enforce security and privacy in these emerging platforms. Okay, so for my approach, I build tools to enforce the desired and secure properties in the emerging platforms by looking into the whole ecosystem with regulations in demand, and also by using technologies such as program analysis for modifications and our security analysis, and also machine learning in general and natural language processing. So we definitely need a diverse set of tools to be able to cover this interdisciplinary and large set of problems. So I'm really proud that my research has getting adopted by many of the commercial platforms and also have impact over the standard. So we hope we can lay the foundation to build emerging secure and privacy preserving platforms, and also on the other hand, to improve the security and privacy regulations. So for this talk, I will majorly talk about 3 parts. The first part is I will talk about how do we build tools to detect privacy violations. So I will talk about how we check the GDPR compliance in the broader plugins. Second, I will talk about how we build tools to detect security violation in the system with mostly closed out systems. And finally, I will talk about looking forward, how can we build scalable privacy preserving machine learning systems? Okay, without further ado, let's go to the first part about checking the GDPR compliance. So as technology evolves, like we have lots of security and privacy concerns in these platforms, and also scandals like Cambridge Analytics, Equifax data breaches in the past years, and security experts and researchers have been increasingly focusing on improve the protections. And among these privacy regulations, GDPR is one of the regulations that's pretty comprehensive for the for privacy regulations. So, and also it was for the first time California regulations will also adapt building on top of it. So GDPR also have a large amount of fines for the incompliance. Like for example, it could be 4% of the company's annual income. So not really profit, but annual income. So that could be a very large fine. But even with this large amount of funds, they're still unclear. Like usually, how these funds, how this works is that some lawyers or some tech-savvy people will work together to identify some privacy violations with the big companies, and then they start to sue the companies. But there's no comprehensive system to really check what system actually, what apps actually violate GDPR or not. So to really get a large-scale compliance check, we need automatic solutions instead of this kind of ad hoc manual check. So previously, there had been some solutions looking into network traffic. I know some of our groups also look into network traffic and privacy policies and cookies, and some of other researchers looking into the user consent. But these are still limited in like when we consider how to evaluate whether a piece of software really violates GDPR or other privacy regulations. We want to understand the whole control flow and data flow in the code so that we can really say, okay, this piece of data actually got shared without users' proper consent. So that's why, like in this paper, we actually hope to check the GDPR regulations on the web plugins. So we choose web plugins because we can get access to their both client-side code and server-side code so that we can have a complete picture. And the challenge is that existing information flow tools, the traversal only limited to single programming languages. But to get a comprehensive understanding about the data flow and control flow, we actually need to cross the different languages like PHP, HTML, JavaScript, and SQL, and even different platforms. So this cross-language data flow is are challenging to identify. So let alone use them to actually detect security and privacy violations, because the variety and involvement of different programming languages. So so our key insight in this work is that so we actually will trying to connect the data flow and control flow across the different languages and map and having an automated mapping with the GDPR regulations so that we can actually check if they violate GDPR or not. Here we select the common articles that have been shared by other privacy laws, such as CCPA. So these articles are directly relevant to data processing via the computer system. So it's also a good fit for us to check by analyzing the code. So basically, for example, like delayed means that if the company actually delays the data after a certain period with the request of the users. So sharing means like sharing the data with first party and third party. whether that's also follow the user's consent. Okay, so this is a system overview of the check plug work. So first, it takes the source code of the WordPress plugins as input and output a list of GDPR violations. So first, it passes and detects language-specific source code. And second, our tool generates basically the CCPG, which is a combination of control flow graph and the system dependency graph. So basically, this is also across the different languages. Especially we're looking to the event control and also data flow. So finally, when we connected it with the cross language, then we'll be able to check it, the GDPR violations. I will show more details. So first, we generate a language-specific code property graph, and we capture all the data and control flow for each of the 4 major programming languages we're going to cover. And later, we connect these nodes from different languages to create this cross-language graph. And at the end, we identify program dependencies across different languages borders. So it helps us to capture the information flow and the control flow in the plugin. Okay, so this is one example. So you can see that in HTML and JavaScript, we actually follow the username relevant information. And we also still were able to check it in the PHP and also in the SQL to connect all the graphs by connecting the cross-language edges, which are the red lines, together. So next, I will tell you more about how do we really check the compliance. So given a piece of GDPR policy or article, how do we actually check it? So these are the major GDPR policies we check. And we specify a set of queries that actually follow GDPR regulation, and we'll check about the violations. Let's zoom a little bit closer into one of example queries. So this query is being used for identify the violations. Sorry, I just dive. So sometimes this is just a little bit format issue when you load the slides into the Google Slides. So for example, this is for the deletion. And if the program actually missing the deletion graph, that means that probably will be a data deletion violation. So this is a simplified example. We have lots of queries to cover different policies in our paper. Okay, so we have manually labeled 200 plugins. I want to notice that we also consult privacy lawyers to actually check question. Yeah. Okay.
Yeah, I have a question.
Sure.
So you're capturing long chains across many different languages. So I'm curious about the usefulness of capturing the whole chain. Could you achieve what you want to achieve by only relying on, let's say, when the data request is sent from PHP to the server, or maybe you can only look at the network request in that case?
Yeah, that's a great question. So indeed, cross-language chains is actually very helpful, at least based on our observations, because lots of times for the data being collected or being shared later or being processed later, they actually cross the different languages. So for example, HTML is mostly the like more on the front end, and there will be some JavaScript to process it, and might be SQL to process the database. So that's why like cross-language is actually pretty helpful to check it. Of course, for if some violations are just limited to one language, our tool can also check it. But it's just much nicer and useful to have a complete picture with a cross-language graph. Does that answer your question?
Yeah. Thank you so much for explaining.
Okay, yeah. Are you talking about this one?
Even
a
better.
little forward.
So when you ask about deletion, your techniques are on the mobile phone, right? They're not on the, or they're on the web server.
And they are on the web plugins. So web plugins, we look into both client-side code and server-side code, both client and server-side code. So that's why we'll be able to know what's going on in their server side as well.
All right, thank you.
Yeah, we actually also think about looking into the like mobile apps because there are probably also lots of privacy violation happening. But the issue is that lots of these mobile apps, you can only decompile their APK and you don't know much about what's going on the server side unless you actually look into the like open source ones. So that's why web plugins is a good example. But I think it's also worthwhile to just look into the client side and also looking at like in a black box manner interacting with the server side, for example, to fit certain data and observe some of the output. That will probably also give you some useful insights. I think lots of times in the closed source world, we need to do lots of black box analysis. So I think that's also interesting. Yeah. Thank you. Yeah. Okay. So we manually analyze the 200 plugins and we consult the privacy experts regarding the GDPR violations. And you can see our performance on this 200 plugins are actually pretty high. So we have lower performance on the sharing because there might be lots of complex paths for doing sharing that sometimes we actually not captured very well in the tool. So the most $1 million question is that how many plugins, what's the percentage of plugins violates GDPR by our check plug tool? Okay, so I want to notice that P-Access is because the web plugins platform, they already have this generic APIs, so users can actually query to get access to their own data. So that's why we just like consider all the web plugins developed with this WordPress framework as following the access policy. But this might be there might still be questions regarding who is really responsible to maintain these access APIs. But for now, we're just considering that they all follow the access policy by using these APIs. And you can see that for the deletion, we have lots of violations, and we also have some violations with sharing and also with security policies as well. So a conclusion for this paper is that the cross-program programming language analysis for data flow and control flow tracking is really important to get a comprehensive understanding of privacy violations in this software systems. And we provide a generic framework which automatically detects GDPR violations. Sorry, I actually should have a link with the tool. But if you go to our paper, we do have an open source link so that you can play with our tool and also our data set. Question? Yeah.
I really like this work. And what would be the effort if I wanted to add an extra? What would be the effort to add an extra plugin to the analysis?
Yeah, you actually don't have to do any manual work because we already have automatical analysis for this cross-language graph generation. So I think if you want to switch to a new platform, you probably still need to like basically build the program analysis tools and connecting the different languages or platforms. But if just adding a new plugin, there's actually no manual efforts, just fully automated in that sense. Yeah.
Nice, thanks.
Yeah, thank you. Yeah. Okay. Any more questions? Yeah.
Yes, thank you for the great talk. A question is like, have you tried to maybe use large language model to like replace part of the method? Maybe, I don't know, like maybe you need to design specific like program analysis method to focus on one tool, but maybe this large language model, they can understand quite a lot of different language and different platforms. So maybe it's easier for you to do it. Have you tried, or what's the ability of maybe it on that?
That's a great question. I think you might be able to use large language models to actually help you to connect to different languages. So to identify patterns about where the edge should be. But one issue with large language model, which we tried it for other security problems, is that it's not that reliable. So you have to verify it if you actually want to use it. Like a method like this, more towards the traditional program analysis, and some of the lightweight machine learning might be more robust compared to the large language model based solution. But large language model could be improving. They could get better, or if you have more fine tuning on the large language model just for your specific purpose, I think they definitely will be able to do something interesting in this space.
Thank you.
Okay. Any other questions?
So my question is about, so some companies like big tech companies like Facebook or Google already like implemented your system. So what about for like small or mid-sized enterprises that implement this? Is something like a difficult for them or relatively easy?
Yeah, I think lots of times that's why for this work we actually look into WordPress plugins. Lots of them, including small or mid-sized companies who probably don't really have a large site or lawyer team to help the developers to comply with GDPR. So I think it's also really important to help these developers. So for example, for the single sign-on work, we also provide our framework to check about their security of the single sign-on, their authentication side, so that they can use it as a service, or they can merge the code into their system. So we should also do more outreach to the mid-sized companies. It's all more about usually these large companies have a security team that's easier to talk to, than the mid-sized teams, just like all developers are taking care of everything. But we do want to make implementing security and privacy systems more approachable, more accessible to developers with limited resources. Yeah. Great questions. Okay. I will next look into how do we build tools to check about security violations. So this one is actually all like black box based. And for this work, we actually look into the messaging protocols between the IoT platforms. So messaging protocols is important protocol for like you smart home devices to communicate with the cloud servers. So it also contains sensitive information, like for example, your sleep pattern or the smart locks code. So here's a typical architecture of the IoT platform. You can see that on the IoT platform, the device and the messaging brokers and the applications, they are actually sending message protocol messages to each other. And the messages are usually critical and including control command messages or any critical authentication information. So this is a simplified messaging protocol workflow based on the most popular standard for messaging protocol, which is MQTT standards. And you can see that the client and broker can use connect and connect message to start a communication. And after that, the app is subscribed to the device topic. Then the device will publish a message and the app will receive the message. So this is typical how the IoT flow works. So there has been ad hocly reported security flaws in messaging protocols, including denial of service attacks, sensitive data theft, and malicious command injections. However, there's still there's still very limited understanding regarding the security of messaging protocols. So in this work, we want to formally verify the security properties in this messaging protocol implementations, which are mostly black box. And for the threat model, we consider two different threat models. The first one is neighboring scenario, where the victim and attacker are in the same network. So the attacker can eavesdrop, drop, or modify or inject messages. The second is the tenant scenario, where the victim uses some devices previously being used by the attacker. So this could including like Airbnb or rental house of secondhand devices. So here the attacker will inject a malicious backdoor into the device, and then when the victim uses a device, actually the attacker can actually launch attacks on the device. Okay, the research question we want to answer here is that how to build a systematic and automatic tool to evaluate the security of IoT messaging protocols. There are two major challenges. The first one is that the messaging protocol implementations are very diverse and customized. So we have many different types of messaging protocol standards like MQTT, COAP, AMQP. And even for the same standards, the implementations on different platforms are also very diverse and customized. So here's an example. Okay, so I think there's some issue here, but basically, you can see that they actually have a very complex parameter. Sorry, this one is actually pretty easy to understand about the topic and message information. But for some of them, they might be more trivial. Like there'll be lots of encrypted fields that you don't know what kind of what kind of the item the network traffic really contains. And another example of customized message protocol implementation is about message protocol interaction logic. So for example, when two devices are connected to the broker with the same client ID, so the former device is kicked offline by Google, and however on Bosch, both devices will be connected. So the second challenge is the complex and closed-off messaging protocol workflow. So even worse, the implementations are basically very closed-off, and it's complex because it's stateful with multiple messages and across 3 parties. So our insights for addressing these 2 challenges is building a property-driven and model-based testing philosophy. So basically, we consider 2 properties. The secrecy property, which means that what piece of message should be confidential, and also authentication properties, which means a set of messages that should be authenticated properly. Okay. Let me show you more examples about. So this is some example logic of the state machine. I think for Bosch. And you can see the broker and devices actually have multi-round. This is even a simplified state machine graph. So you can see that in the state machine that the message will trigger the transition from one state to another. So we call this transition logic also as interaction logic. Here's a brief overview of the platform. So before the formal modifications, we apply 2 automatic modules to actually construct the state machine, which is very critical. Due to the time limit, I'll mostly focus on how do we actually construct the state machine automatically from the closed-source implementations. So first is that extracting customer message semantic is non-trivial. So we need to combine both traffic and document-based analysis, and also a combination of NLP and pattern matching for that. So for example, here, the will message is in the JSON format that contains key value pairs. So basically here, the key username indicates the value semantics, so that's more straightforward. But some parameters are more hidden in the traffic, which is non-trivial to extract. Like, for example, some of them might be encrypted. In this case, we found that IoT platform document is helpful in telling us what the parameter might mean. But we need to combine the 2 analyses together. I would say this is probably a good answer to your question. Previously, we used more NLP based analysis, like part of speech dependency parsing. But now, like using LM, you probably will be able to get like better results, but not necessarily more reliable results. So combining the traffic analysis and document analysis, we're able to construct this map of the semantics for different fields in the traffic. The second important step is trying to extract interaction logic. So here we apply active model learning to infer the interaction logic. Like we have membership queries and also equivalence queries. So basically trying to collect the response to the input to refine, like basically equivalence queries will be finding counterexamples. And because we have some assumptions about how the state machine might look like based on analyzing the document of the messenger protocol and also IoT platform, but that might be different from what's really implemented in the system. So we also need to have equivalence queries to identify counterexamples so that we can refine the membership queries to change the state machine to be closer to the reality. So there are also lots of caveats. So for example, the current tools usually only support 2 parties and the response messages. So we build an adapter to support multi-parties and monitoring the connection state to maintain the stateful machine. So and also the equivalence query is really time consuming while dealing with multiple types of messages, because it's actually trying to try out all the possible sites. So basically we build a customized equivalence algorithm to cut down some useless queries. And also sometimes model learning might be trapped into endless procedure. We also built a smart stop learning system algorithm to stop it. Another thing I want to mention is that, especially it's important for security, is that we need to model validity predicates. So validity is usually trying to use to verify, like for example, if the current delivery ID less than the former delivery ID, or if the password is being validated. So we design carefully about how we mutate a message and observe the output to trying to decide about validity predicates. So to summarize our evaluations, we evaluate 10 messenger protocol implementations from 9 leading IoT platforms. So we test 4 kinds of protocols. It's a 10 MP implementations on 9 IoT platform because one IoT platform actually have 2 protocols implemented. And we tested our own services that we constructed together because of the ethics of the testing and validated all these attacks on our own devices. So we uncovered 11 types of messenger protocol attacks. You can see lots of them actually cause serious impact. This is one example, unauthorized response topic published so that attacker can actually inject malicious comment by this response topic published message. To summarize, this is the first systematic and automated framework to evaluate the security of messenger protocol implementations. So this is large-scale experiments on the actually 4 popular messenger protocol standards on 9 leading IoT platforms, and they actually impact the millions of users. We also have this open source code for you to play with. This one also have real-world impact, like Tuya Smart, which is a major IoT manufacturer in China, adopting our messenger protocol security check inside their own security check as well. And so one thing I want to point out is that this works mostly based on black box analysis, and only 2 platforms are actually open source, which we can actually have some ground truth regarding the false positive and false negatives. But it's good that Tuya Smart actually using our tool internally. Based on their feedback, our tool is still pretty accurate. So indeed, there will be some cases that we really don't know what's the semantics of the message, but it doesn't seem to impact mostly overall security of the protocol implementations. All right, so I should stop at 10, right? So so I should stop at 10, right? Yeah, okay. So since we have still have a little bit of time, I will go over the final work. looking forward, how do we build scalable privacy-preserving machine learning? Because this will enable us to have better privacy regulations and also to remove some burdens of having to share some very sensitive data to companies that you might not really trust. So privacy is really critical for this data-hungry machine learning algorithms. For example, this is if the patient has sensitive medical images, he or she want to get the diagnosis, but without really disclosing more information to the hospitals. And the hospitals also, like hospitals also don't want the patient to know about the machine learning model because that's proprietary, right? So basically, privacy preserving machine learning want to do both. For that's the first scenario we'll talk about is inference. But for the training side, it's the same privacy requirements, but training usually much more computation intensive because of input data are processed in batches, and they have actual back propagations that to update the model. So we use one of the most commonly used SRAM model for secure multi-party computations, which is called three-party semi-honest security with honest majority. So here, okay, so here the honest majority means that allowing a single semi-honest party for corruption. And semi-honest means that corrupt parties still follow the protocol, but is curious, trying to gather more information. There have been lots of constructions in recent years regarding like multiple parties jointly compute a function will keep each of the input private. You can think about this secure multi-party computation as a special way of encryption that allows you to do calculations on encrypted data. Okay, so I already tell you that the current state of art is very slow. And I'll also show you how we actually get like over around 40 times improvement on this. So basically, now that the machine learning, this is adopted from OpenAI, so machine learning get into the modern era when people actually switch from the GPUs. So the hardware is really important for the hardware solution. And so our intuition is that previously CPU training is also very slow, but GPU is improved significantly. And also we look into the state of art, privacy preserving machine learning, and 98% of the training time actually coming from linear layers. And the linear layers are actually very easy for, or very suitable for GPU to accelerate. So our idea is that why not we also use GPU acceleration for privacy preserving machine learning? So we built the first secure multi-party computation framework where all computations are performed on the GPU. So this work is a system that supports end-to-end private training and inference on the GPU. And also we build new abstractions and protocols to embed MPC operations on the GPU. So these things are non-trivial because we need to design the best protocol that are most suitable for GPU accelerations. So our tool are built based on PyTorch and Encrypt10, and it achieves up to 3.7 times improvement on private inference, but up to 37 times improvement on the private training, which is much more computationally expensive. So this is the overview of our system design. So we embed, we have 3 pillars. First is embed integer operations into CUDA. That's because like floating point arithmetic is very common in GPU, and GPU are very good at it. But most of our crypto algorithms are on integers. So we actually use bilinearity and actually be able to convert the large integers into sums or products, small integers, and do similar operations on metrics. And the second pillar is we choose replicated secret sharing as the basic building block. Replicated secret sharing, I won't go into too much details. It's a type of additive secret sharing. The reason why we use it is that it's actually pretty friendly to be scalable on the GPU. It's easy to do it parallel. And also, finally, with the first two pillars, we can already do GPU-friendly protocol for linear operations. But it's also important to improve the performance of nonlinear operations. So basically, the design motivated from like, so what GPU is good at? So GPU is good at component-wise operations like metric additions and multiplications, but operations with lots of control states are slow. And we also have memory limits. So we want to design the protocols that's highly scalable and also less memory consuming. So classical methods such as gobble circuit is not suitable because of conditional statements and high memory consumptions. So basically, this is also a few design choices we make for doing like shared conventions and do private comparison so that we can do ReLU function. I won't have details, go over the details. I don't have time to go over the details, but basically, this only requires addition circuit and also improve the private ReLU, although it's non-linear, but also 10 times faster on the GPU. So I want to highlight a few results. So we tested with the inference because with our current design, we can do batch inferences. So it's even better if you do it in a batch in our method. And training time is a huge speed up of 37 times. And also we also evaluate inference accuracy because when we deal with the nonlinear protocols, there are some approximation we did, but it looks like these approximations are actually only included a very small amount of noise. So the inference accuracy is exactly the same with our private training and without private training and inference. And also for the training accuracy is also the same trend. So to summarize, this is a really important step to move privacy-preserving machine learning to model machine learning models. You can tell there that there's still a far way to go to from like now around 40 times speed up. We can do it. We can do the training SNet model on tiny minute with encryption in 9 days. That's still pretty slow. And some of my students also doing more work in this domain, so that we are also looking to like transformer models, larger, more like recent models, like how can we do it in a reasonable way for the privacy preserving machine learning. And there have been lots of follow-up work on this domain as well. I think our crypto GPU work has become the de facto framework that people would compare with and build on top of for GPU-based privacy preserving machine learning. You can also check out the code here. And also Facebook Crypt10, which is also a popular privacy preserving framework, now actually use Crypt GPU for the GPU part of privacy preserving machine learning. All right, so this is an overview of my research, and some of you might be talking to some of my students, so it'd be nice to have more detailed discussions. And I want to acknowledge my collaborators and research sponsors. And I'm always open for great collaborators and students. Feel free to contact me. I think for building secure and privacy systems, especially in a regulated way, we actually need to across different layers and also reach out to different stakeholders in this ecosystem. Yeah. Thank you very much, everyone, for coming to my talk. I really appreciate your time. Yeah. All right. Do we have more questions? Yeah.
There's one question online. Emiliano, you want to talk or you want me to read your question?
Oh, okay. No, I can talk. Thank you.
Yeah, yeah,
Hi, thanks for the great talk. Yeah, I just had a question about the last part. So besides looking at the computational overhead, have you also looked into monetary costs, monetary overhead of using, these kind of GPU accelerated schemes? I think that's also maybe an important aspect. Thank you.
Yeah, that's a great question. So basically for the experiments we are doing, we didn't really cost the amount of money that we used, but we did use so for building a prototype, we use our own GPU servers, but for running experiments, we also use AWS so that we can have a more like apple to apple comparison to some of the previous work. I don't remember how much money it costs. It must not be a lot. Otherwise, I would really remember it because I actually reimbursed for the cost. But I think your question is more towards like, for example, can we like, is there a way to actually make it more like cost less for the GPU-based accelerations? I think if we want to further like reduce the cost of the training and classifications, maybe we can first do some model distillation instead of just using the standard models, because lots of compressed smaller models still have the similar performance. So that's probably a better way of doing it. Another way is that trying to think about if you distribute all the computations in more servers, in more lower end servers, whether you will still be able to get similar performance. I think that question probably depends because there might be more communication overhead if you have a lot more parties. So yeah, so these are just some my initial thoughts, but feel free if you have more comments on that. Yeah.
Okay, thanks so much.
Yeah, thank you. I don't know. Yeah.
Do we have more questions? So if not, we can wrap up, and then we can stay around here for those in person and talk more to the speaker. And let's thank again our speaker.
Thank you so much, everyone. Thank you.